Hello, and welcome to section 4.4, L'Hopital's Rule and Indeterminate Forms. In this section, we're going to go back to limits again, and we're going to look at a rule that we can use that involves differentiating to find limits. So because we'll be looking at finding limits again, you're going to need to remember some of those limit laws, or actually all those limit laws that we covered in Unit 1. And so just, if you're rusty on those, review these items. So this rule called L'Hopital's rule is used on limits that are called indeterminate. So there are certain limits that we couldn't find because we couldn't apply the limit laws that we'd learned. For example, the quotient rule. If the limit in the quotient is 0, we cannot apply the quotient rule. And there are some other results that are called indeterminate because it either leads to an ambiguous case or we're not sure just how to handle it. So you have a limit that is going to result in something looking like this. These are indeterminate forms. If you try to evaluate a limit and you end up with 0 over 0 or infinity over infinity, or even one function's going to infinity and you're subtracting another function that's also going to infinity, yet these are examples of something called indeterminate forms. Use L'Hopital's rule on these 6 indeterminate forms. So let's look at a few examples of stuff that we've, shouldn't look too weird that we've seen in the past that are actually indeterminate and that we've just found the limits like graphically in the past. Limit as x goes to 0 of sine of x over x is of the indeterminate form 0 over 0 because sine x is going to 0 obviously as x goes to 0 and so is that denominator. So we can't use the quotient law because that denominator is going to 0. So we didn't know how to solve this unless we used something like the squeeze theorem or looking at it graphically. This limit, as x goes to infinity of ln of x over x, that's of the form infinity over infinity because ln of x is growing without bound as x grows without bound, right? And so is that denominator. But the thing is, we don't necessarily know that this limit's not defined, even though it's of this indeterminate form, because, depending on how these functions in the numerator and denominator behave relative to each other as x goes to infinity, that's what really determines what the limit is, the ultimate result. And then another example of the form infinity minus infinity would be this limit. So we're going to take a look at using L'Hopital's rules on functions, limits like that. So here is statement of the rule. A lot of people say la hospitals because it looks like the word hospital is in there, and this is French, and I don't speak French, but I've heard that it's not pronounced la hospitals rule, it's L'Hopital's. Another spelling you might see is without that S, but there's a little mark over the O, mark that looks like this over the O. That's another form of this spelling. But this rule is used when we have an indeterminate form of the form 0 over 0 or infinity over infinity. And it states if you have a limit, quotient of functions, and the limit of the numerator is going to 0 and the limit of the denominator is going to 0, or the limit of the numerator is going to infinity and the limit of the denominator is going to infinity, and it could be either sign of infinity, then you can evaluate the limit of the quotient by taking the derivative, the quotient of the derivative of each function. So this can be a little dangerous if you think back to the quotient rule for differentiation. Remember, when you find the derivative of a quotient, you don't just take the derivative of the numerator and the derivative of the denominator. There's that quotient rule. But here with L'Hopital's rule, in the context of finding a limit, that's exactly what you do. You take the derivative of the numerator and the derivative of the denominator. Is only used for finding limits of certain quotients, again with those conditions of 0 over 0 or infinity over infinity. And we're going to see that if we have a problem where we don't have a limit that meets those criteria, we can do some algebra to put it into the form where it will be 0 over 0 or infinity over infinity, and we'll look at examples. So here's an example from the text. Use the graph of f and g and their tangent lines at the point 2, 0 to find this limit. So I don't know what f is. I don't know what g is. I know what their tangent lines are. Those are the dashed lines here in the graph. And so to use L'Hopital's, we need to make sure the conditions are met. We have f and g are obviously both continuous from the graph. And since they're continuous, the limit as x goes to 2 of each of them is equal to, I can just evaluate the function at 2, because that's, remember, the definition of continuity. And so that limit is 0 in each case. So this does meet the criteria for L'Hopital's. So to find the limit as x approaches 2 of this quotient, I can find the limit as x approaches 2 of the quotient of the derivatives. What's f prime and what's g prime? Remember, that's the slope of the tangent line. And we're given the tangent lines here. So the slope of the tangent for f is 1.8, and the slope of the tangent for g is 4/5. So then we have that this limit is 2.25. So this example involved remembering what the definition of a derivative was at a value, and remembering what the conditions are to apply L'Hopital's rule.